Hey, welcome back. We're going to continue in Chapter 1. We're going to start classifying numbers and then graphing them. So our objective for today, Lesson 1.4, Objective Day 1, I will review the classification of real numbers and then graph them on a number line. So here we go. Natural numbers. Natural numbers are the counting numbers. It's how we count rocks, it's how we count money, it's how we count things, objects. It starts with 1. Natural numbers start with 1. There's nothing less than 1. Then they go up in whole numbers. You have 1 piece of cake, 2 pieces of cake, 3 pieces of cake, 4 pieces of cake, right? Those are the natural numbers. Whole numbers are every natural number, and then in that set they include the number 0. They include the number 0, right? Notice that every natural number is also a whole number, but not every whole number, in particular 0, is a whole number, but it is not a natural number. So not every whole number is a natural number. On a number line, the natural numbers are these top ones. I'm going to switch to my pen. Natural. Down here are the wholes. Look at how they cross over. The only one that doesn't have a double dot on it is 0. That's because it is only whole. Everything else are both natural and whole. So if you have natural, then you also have a whole number. The next classification is an integer. The integers include all of the naturals, 0, and then the opposites of the naturals. So we have the naturals, 1, 2, 3, da 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 da, keeps going, right? We have 0, and then we have the opposites of all of the naturals, -1, -2, -3, -4, -5, -6. Those are all integers. There's no -1.1 or 10.2. It's just, they're just the wholes and then the opposites of the naturals. Again, every natural and whole is also an integer. Every natural and whole is an integer, but not every integer is a natural or a whole. Okay? On the number line, this is kind of how things play out. The naturals start at 1 and go to the right in increments of whole numbers. The wholes start with 0 and go to the right in increments of whole numbers. The opposites of the naturals start here and go left, right? Together, collectively, these are the integers. These are the integers. All right? Positive numbers allow us to count. They allow us to measure an increase in a value. They allow us to state a value above 0 or an increase, or in business, they represent a profit. A profit. Okay? An integer, a positive integer, is used to express numbers that are going upward. They have an upward progress. So if you start with a positive number, in order to write it as an integer, you're going to add a positive sign and you're going to round to the nearest whole number. Remember, integers have to be wholes. Okay? And then they can have a positive or a negative, all right? So we're going to add the sign. When we're talking about positive numbers, we're going to add a positive sign and round to the nearest whole number. So let's look at example A. We want to write as an integer that from 2004 to 2005, the population of the U.S. increased, so that's going to be a positive integer, by about 2,845,000. So we're going to write it as plus 2,845,000. Now, I'm going to write it over here. Positive 2,845,000. Okay. This is a whole number. Now look at example B. On Monday, the Dow Jones Industrial Average closed up, so that's a positive, 52.59 points. We want to write it as an integer. This is not an integer because it has partial. It has a decimal point, all right? So this would be plus, and we're going to round up to the nearest whole number, plus 53. That would be the integer to describe this, all right? Example C. Why don't you try this one and come back? Right, welcome back. First quarter 2012, Acme Company earned $796.3 million. All right, so we're going to write it as a positive 796 million. This could also be a positive 300,000. Right? That would be the integer. Negative numbers. They allow us to correctly describe a decrease in a value below zero, or a business loss. In the next examples, use an integer to express the underlying number in each application. The lowest, example A, the lowest Fahrenheit temperature ever recorded was 129 degrees below zero. We want to write 129 degrees below zero as an integer. Below would be minus, negative 129. There's the integer. Example B, the shore surrounding the Dead Sea is 1,340 feet below sea level. Below sea level. That's a negative number. Negative 1,340. Try example C and D and then come back and see if you got it right. All right, welcome back. From 1995 to 2005, the number of TV cable systems decreased by 2,809. Decreased by, that's a negative number, 2809. Example D, the temperature dropped, went down, went in the negative direction, 24 degrees in 6 hours. This is negative 24. That's the integer that describes a drop of 24 degrees in 6 hours. All right. The next type of number that we can classify are rational numbers. Rational numbers include naturals, whole integers, plus they also have the what I call the in-between numbers. Fractions. Fractions that are an integer over an integer, such as 3/2, 11/4, negative 3.5, because that's the equivalent of negative 7/2. Rational numbers also include the decimals that terminate. I want to write that word in there. That end, that terminate. If they end, they terminate, such as 0.25. That is a terminating decimal. It doesn't go on. It ends at 2 decimal points. Or 1.37. I'm sorry, 0.137. The next form of decimal are the ones that repeat. The ones that repeat. Decimals that repeat. Decimals that end, decimals that repeat. They're rational numbers. Okay? Look at this one. negative 4.567567. Notice how the 567 keeps repeating. So we write it as negative 4.567, okay? With a line over the top. Now look at this example, 0.11111. It just keeps going, 11111. These ellipses aren't saying that these ellipses don't tell you that you have an irrational number, okay? This is a repeating. So that means we can write this as 0.1 with a line over it. 3.34. Okay? Notice how the 3-4 just keeps repeating. 3-4, 3-4, 3-4. So we can write this as 3.34 with a line over the 3.34. Now if we're to graph these, we would, here's 0, negative 4 is over here, and we have to go even further to the left, 0.567 more. So here's the estimate for negative 4.567 on a number line. 0.1, well that's just a smidge to the right of 1. This is repeating, right? So here is an estimate. 3.34. We have to go to the right of 3, but not all the way to 4. Okay? Notice that every natural, whole, and integer is also a rational number. If it's rational, it's also integer, whole, and natural. Okay? But not every rational number is a natural, whole, or integer. Okay? So what this says is if I have 0, it's a whole, it's an integer, and it's rational. All right? If I have negative 1, it's an integer, and it's rational. But if I have negative 5, all right, I'm sorry, negative 4.567, that is only a rational number. Only a rational number. It's not an integer, it's not a whole, and it's not natural. So every natural, whole, and integer is also rational, but not every rational is a natural, whole, or integer. Okay? Definitions, again, of an irrational number. These are the other set of in-between numbers. Okay, these are the numbers that you cannot make a fraction out of by putting an integer over an integer. Okay? They don't work out that way. Okay, if it's an integer over an integer, then it's rational. These you're going to see as never ending and never repeating decimals. Never ending means they're non-terminating and non-repeating. And when you look at them, they have decimals and it just keeps going. There's no pattern. See how there's no pattern to this? And then you have ellipses behind it. Okay? You have values such as pi. Base E. The square root of 2, the square root of 5, the opposite of the square root of 13. Notice that all of these, the radicand, are non-perfects. So the square root of non-perfect squares are always irrational. Square root of non-perfects are irrational. If we were to graph these on a number line, pi is 3.14. So we would put a dot here. This would be pi. E is 2.71. So it's like here. This is E. The square root of 2 is 1.4, 1.14. .41. the square root of 5 is 2.2. The opposite of the square root of 13, well, the square root of 13 is going to be between the square root of 9 and the square root of 16. The square root of 9 will be the opposite of 3, and the square root of 16 will be the opposite of 4, so it's going to be right in here, the opposite of the square root of 13. Remember that for irrational numbers, any decimal representation is just an approximation because they actually never end. It just keeps going and going and going and going. This is like a flow chart of how the real numbers exist in relationship to each other. The real numbers are made up of irrational and rational. If your number is irrational, that's all it's going to be, is irrational. If it's rational, it could be, rationals are made up of integers and fractions or terminating and repeating decimals. So if you have a rational number and it's a fraction or a terminating or repeating decimal, then all it is a rational number. However, if your rational number is an integer, then it could be a whole, or it could be the opposites of the wholes. All right? If it's the opposite of the wholes, or the negative of the naturals, then it's an integer and a rational number and real. All right? The wholes could be a 0, okay? Or it could be the naturals, right? If it's 0, then it's a whole. If it's a whole, it's an integer. If it's an integer, it's rational. Determining if a number belongs to a set. All right, we're going to list the numbers in the following set. This is our set of numbers here that belong to each classification of numbers. So A are the natural numbers, all right? So you want to make sure that if you have any perfect square roots, you go ahead and you simplify that. Sorry. This is the same as a 5, right? So now I'm looking for natural counting numbers. Is -5 a natural counting number? No. -2/3? No. 0? No. Square root of 2? No, that's an imperfect, or yeah, non-perfect. 3 1/4? No. 5? Yes. 5.8? No. So the only natural number there is the number 5, or the square root of 25 is a natural number. The whole numbers are going to be any natural numbers. I have the square root of 25 and 0. Okay, well I have that, and 0. The integers are going to be all of the whole numbers. So I have the square root of 25 and 0, and then any negative or opposites. So then I have -5. The rationals are all of the integers. So I have the square root of 25, 0, -5, and then I have any terminating, repeating, or integer over an integer. So I have -2/3, 3 1/4, and 5.8. The irrational numbers would be square roots of non-perfects, so that's the square root of 2. Do you have any non-terminating, non-repeating decimals? No, so this is the only irrational number. And then the real numbers are all of them. negative 5, negative 2/3, 0, square root of 2, 3 1/4, square root of 25, and 5.8. Determining order of numbers. So this is like being able to place them on a number line. When you're comparing numbers and plotting them on a number line, remember, left is less. Left is less, okay? And right is richer, or right is greater, okay? Positive integers are intuitive because we have been working with them since we learned what a number was. But negative and fractions or decimals can be trickier. So which is less, negative 4 or negative 3.5? Well, I'm going to mark 0 on my number line here, right? And then I'm going to mark negative 4. Negative 1, negative 2, negative 3, negative 4. Right? Now, where would negative 3.5 be? Well, here's negative 3, so I have to go even further than negative 3. So here is negative 3.5. Sorry, my pen just doesn't want to make. Here's negative 4. So which one is less? Negative 4, because left, negative 4 is to the left of negative 3.5. Which is less, negative 1/2 or negative 1? Well, let's say that this is 0. This is negative 1. So I'm going to put a dot here. Now, where would negative 1/2 be? Well, it's going to be between 0 and negative 1. So here's negative 1/2. Which one is less? It's the one to the left. So that means negative 1 is less. All right? Why don't you try the last two on your own and then come back and see if you got it right. All right? Welcome back. Okay? Negative 3 is to the right of negative 7, so negative 7 is to the left. That means negative 7 is less. Left is less. Which is less, 4/5 or 5/9? Well, here's 0. This is going to be close. Okay? 4/5, if that was 5/5, that would be like 1, right? So 4/5 is here. This is 4/5. Okay? 5/9, if that was a 10, that would be a half, right? 5/10 is a half. So this one is right about here. Whoops, in the middle. Sorry, I'm trying to make one in the middle. And that's 5/9. So 5/9 is to the left. Left is less. These are the problems we're going to be working on in class tomorrow. So go back over the notes if you need to. Come with questions. And I will see you tomorrow. Thanks for listening.